In this video, we're going to be looking at this sequence of numbers. So we start by filling up the first row and first column with ones, just like with Pascal's triangle, except that's a triangle and this is a square. And then kind of like Pascal's triangle, we add up the surrounding entries to get the next one. But instead of just adding the two neighboring entries here, we're adding the three entries up left and diagonally up and left. So for example, to start out with, we would have 1 plus 1 plus 1, which gives us 3. And then to get the next entry down, we have 3 plus 1 is 5. And then similarly, this one is 1 plus 3, which is 5. And then adding these together gives 5 plus 3, which is 13, and so on. So I filled in the first 36 entries. So our goal is to find a formula for the entry in row M and column N. So there isn't really a closed form in the sense that it's a simple formula that you can just write out. But there are some formulas that let you compute these things pretty efficiently. Okay, so we're going to call these numbers A, M, N for row M and column N, although it's symmetric, so it doesn't really matter which is M and which is N. Okay, and our recursion, well, first of all, we can think of all these entries out here as being zeros to make the recursion work even for the ones up top and on the side. Okay, so our recursion says that if I take AMN, I get that from adding the entries to the left, up, and diagonally up and to the left. So the entry to the left is a M n minus 1. The entry to the diagonally up and to the left is n minus 1, n minus 1. And then finally we have a m minus 1, n for going up. Okay, and we can have the initial conditions that a of m0 equals a of 0 n, which is 1 for any non-negative m and n. Okay, so our goal is to find a formula for these a, m, n's. So the trick that we're going to use is to apply generating functions. So we want to look at, well, it's going to be a two-variable generating function because it depends on two inputs. So I'm going to attach this to x to the m, y to the n, and I'm going to sum over all m and n non-negative. Okay, and this is going to be my generating function f of x, y. Okay, and now we just have to figure out what the recursion says. So our recursion, well, first of all, when m is 0 or n is 0, I get 1. So if I just have either a constant term or just x or just y, those are all 1s. Now, for the other terms, I'm going to take this recursion here and multiply through by x to the m, y to the n and see what I get. Okay, so I get, I'm going to omit the indices for now, or rather the bounds on the indices, just because it's a little annoying. So a, m, n, x to the m, y to the n. So that sum is the same as a m minus 1 n plus a m n minus 1 plus a m minus 1 n minus 1, and that's all times x to the m, y to the n. Okay, so now we just have to figure out what to do with all this. Okay, so am minus 1n is going to be, well, I'm shifting m by 1 and I'm leaving n unchanged. So actually what I can do is just write the sum of am minus 1n. Actually, my to the n is the sum of a m n, but now I shift m up by 1. Okay. And well, I do have to be a little careful about the lower bounds on m and n. Well, n is the same, it's still any non-negative number. And well, for m equals 0 up here, well, I don't get anything meaningful. I just get a 0 essentially for a of minus 1 n. So I can really start m at 1, which corresponds to starting m at 0 in this new sum. So it's actually the same range as before. And now I just do the same thing with the other terms. Okay, so I get that sum plus, again, over all non-negative m and n, a of mn, but this time I shift n up by 1. And then finally I shift m and n both up by 1. Okay, so what do I have? On the one side, I have, this is just my original function f, and then this term is f, but now I have an extra x. This term is f, but now I have an extra y, and now I have an extra xy. So what this is really saying is that f of xy equals x plus y plus xy, f of xy. Okay, well, almost. Because I am actually missing one term, which is the constant term. So I won't ever get the constant term from any of these sums. So I have to add that on. So I'm going to get a plus 1 there. Okay, so what does that give me? What does that give me? I move everything over except for the 1. I get 1 minus x minus y minus xy, f of xy equals 1. Okay, so f of xy equals 1 over 1 minus x minus y minus xy. Okay, and this is my sum of a m n, x to the m, y to the n. Okay, so now I just have to find a way to extract the coefficients from this. Okay, so there are a couple ways of doing this. One is to just kind of take this thing here, and I have 1 over 1 minus that, so that's a geometric series. So this is a sum over k from 0 to infinity of x plus y plus xy to the k. Okay, and now I want the coefficient of x to the m, y to the n. So first I should see how I can actually get a term like that from taking the kth power of this thing. So I'm going to have some number a of x's, some number of y, say b, and then I'm going to have xy to k minus a minus b. Okay, and I want this to be equal to x to the m, y to the n. Okay, so what does that give me? Well, I equate the exponents, so m is, well, I have an a x's and then k minus a minus b x's, so m is k minus b, n is k minus a, so a is k minus n, b is k minus m. Okay, and now I just look at the coefficients. So I need k minus n x's from expanding this, k minus m y's, and then the rest will be xy's. Okay, so in general, the coefficient of x to the a, y to the b, z to the c in x plus y plus z to the k is, well, it's a multinomial coefficient. So I have k variables, but a are all x's. So I have to divide by a factorial to account for the overcounting from the permutations of the x's. And then I divide by b factorial and c factorial for the same reason. So I get k factorial over a factorial, b factorial, c factorial, which is often written as a multinomial coefficient like this, kind of like the notation for binomial coefficients. Okay, so putting this all together, what we get is the coefficient of x to the m, y to the n in, well, I replace z with xy, and I get k factorial over, now what was a, I had k minus n x's, so I have k minus n factorial, and then I had k minus m y's, oops. Okay, and then finally, how many xy's? Well, k minus whatever that is. So these two add up to 2k minus m minus n, and altogether I need a k, so that's m plus n minus k factorial. And as a quick check, you can verify that the denominators, those terms add up to k. Okay, and then we just take the sum over all k's. Well, with most k's, we'll get 0, but that doesn't matter. So amn is the sum over all k's of k factorial over k minus n factorial, k minus m factorial, and then m plus n minus k factorial. Okay, so it's not a very pretty formula, but each of these things is an integer. And well, if k is smaller than m or n, you're going to get 0. And if k is bigger than m plus n, you're also going to get 0. So you actually have a pretty small range of values of k, where this gives you something non-zero. Okay, so that's one formula. Maybe I'll box it just because it's one of the answers we're interested in. Okay, now there's one other nice little way of finding AMN. So let me go back up here. Okay, so before we took this x plus y plus xy and used a geometric series, but we could also use a geometric series in a different way. So let me go down and rewrite this function. So remember, we're starting with 1 over 1 minus x minus y minus xy. But this gave us x plus y plus xy and powers of that, and that's kind of annoying to deal with. So what we could do is add and subtract 1 in the denominator. So we get 1 over 2 minus 1 plus x plus y plus xy. And now the great thing about this is that the denominator, well, this piece factors as 1 plus x times 1 plus y. So this gives us 1 over 2 minus 1 plus x, 1 plus y. Okay, and now we can use another geometric series, but the terms will be a little nicer this time. So we'll get 1/2 over 1 minus 1 plus x, 1 plus y over 2. Okay, so now we expand this as a geometric series. And that gives us the sum from k equals 0 to infinity of 1 plus x to the k, 1 plus y to the k over 2 to the k plus 1. Okay, and now it's pretty easy to read off the coefficient of x to the m, y to the n from this. So I have, from here, I have a k choose m for x to the m. And from here, I have k choose n in front of y to the n. And I sum over all k's to get the total contribution. So the total coefficient of x to the m, y to the n, which is amn, is the sum over all k's of k choose m times k choose n over 2 to the k plus 1. Okay, so we get two very different looking formulas for amn. And you can use this to get some pretty wacky identities. So for example, well, one thing you can tell immediately from these formulas is that this thing here is always an integer, which certainly isn't clear just from looking at it. But if you try it, you will get only integers. And another thing is that, well, we have a really quick way of computing these AMNs, just either using the recursion or using this closed form in terms of factorials that we had. And so you could get weird identities, like for example, way back at the beginning, we had A55, which is 1683. So if we go back down, we can plug that in and get a weird identity for free. So we get A55 equals the sum over all k. Now, I won't get any contributions from k less than 5, but I'll just keep the indices starting at 0. So I get k choose 5 squared over 2 to the k plus 1, and that equals 1683. So that's a pretty bizarre identity that would be hard to prove with other methods if you didn't know this trick.